Welcome to our third contest problem analysis session. The first question we're gonna cover is 8 of binary tree. I think most of you have solved this question, right? Anybody who didn't solve this question? I didn't expect that. Okay. Okay. From the ones who solved this question, who want to cover it on the board?
So this problem, I think it's the way I solved it. It's easier if we use recursion. The way we use recursion is our base case is if the leaf node, if the recursion gets to the leaf nodes, which is if it gets here. But to understand it, let's just start from here. So we have the root, right? Now we're going to calculate the height of this and the height of this, and we're going to take the max one, and then we're going to add 1 to it. So we're always going to do this. When we get here, we're going to calculate the height of this tree, and then we're going to calculate the max, and then we're going to add 1 to it. This is how we're going to solve it. And yeah, I think this is the base case is if we get to the leaf nodes, and then we'd go back up the recursion. So when we try to solve this, when we go to the left direction, let's go to the left direction. We have we go there, and then we try to solve it, and then we go here, and we have 1. So we have 1 here, and then we also go here to the right tree, to the right edge, and then we also have 1. The max is 1. So when we add here, 1 plus 1 is 2. And same thing, we go here, we have 1, and then we try to solve this, and then we try to solve this again, and then we have 1. And then there's no other leaf here, so we go up one node. So we have 2 here. We calculate the max. We have 2 max. So when we add it here, we have 2 plus 1, 3. So we calculate the max of these, and we add 1 to it. So we have 4. I hope you understand the logic of what I went through. Does anyone have questions?
Can we also do time and space complexity analysis?
So I guess in this case, time complexity is O of n being the number of trees, the number of nodes in the tree, and space complexity. I guess that's also O of n.
O of n?
Yeah.
Why?
Because like we're going to store every elements in the tree as a variable.
Or you can think of like they are passed as parameters to your function. So if given tree, how much additional memory you are introducing?
Actually,
because the tree has to be given, right? Otherwise, how would you talk about it? Right, constant memory actually.
The cool stuff behind the recursion.
Yes.
So we might need to.
Oh, the call stack. Yes, very good point.
Since we have the call stack, at a time we have to store at most the height of the tree on our stack. So we don't store all of the elements in the stack because after calculating this, this value will be removed. So log in will be the space complexity.
Or the height of the tree.
Or the yes.
Isn't that the base case?
Huh?
Isn't the in the base case for the space complexity?
Yes.
So
what's the worst case?
What would be the worst case?
It depends on the tree. If the tree is linear, like in one direction, we have to store all of it. So it will be a linear time, linear space.
Oh, yeah.
Oh, yeah. Okay. Any question? So everybody feels confident to implement the solution. Okay. Okay. Any different approach for this question? So he implemented with recursively, and it can also be implemented iteratively. So is there anyone who wants to show us how we can implement this iteratively?
No, but we can even keep a track, and also in addition we can save the actual size, meaning the stack will hold the element itself, the root, or the node we will hold in, and the current level we have. So we have for 0 at first. Then, until the stack is empty, we pop it out and also save its children. So we pop 4 and O out, and every time we do, we increment the level. So for O is out, then its children are 2, and the level, since we went 1 down, it will be 2, 1, and the other child is 5 and 1. Then we keep doing this. We pop out the last element we added, meaning I think it's, yeah, we can pop out 2, 1, and when we pop out 2, 1, we do the same thing. So 1, 2, and 3, and we keep doing this, and every single time we have to keep track of the maximum level we have. So once we do all of this, we return the level, and this would hold the stack size of n being the number of nodes, and time-wise, since we're going over all of the nodes, it will also be of n. Does that make sense? Any questions?
Why do we have to go all of them? Like, can't we just keep max? Because the max is going to be the depth.
No, the stack at any point it might be like, I think, all the level. Yeah. Maximum it would be like of the level.
Oh, I see. To
The
keep
stack.
track of yes.
So the space at maximum would be the length of the last level. Yeah, that would be it.
I also come up with another idea, which I didn't implement, but I can maybe show you.
Yeah.
We can also use the. Actually, it's maybe early to mention, but we have a BFS algorithm, which also uses Q. So we will start from the root node, and we will say, like, for example, we will hold the depth in each node. So for our children, we will say, like, while processing them, we will say we will just add 1 to the children, and keep going this, So each time we process our children, we just say you are at a deeper level than me, and we are also saying, like, we are keep track of the level depth. Then we can just return the maximum level, which is very similar to this idea, just using Q instead of stack. But since it's gonna take a lot of code base, that's why it was easy to implement in recursively. That's why I did that.
So as you can see, it can be implemented iteratively. It's just simulating how the recursive works. And for implementation, I think the recursive one is easier and shorter. Okay. If there's no another question, you can continue. Okay. Who solved this question? And others. Pardon? Sparse Array. Who? Okay.
Okay. So the question basically asks, we have given an array of strings, and we have given an array of queries. Those are also strings. So it just asks, for example, for each query, for example, AB, let me. How many times this query occurring in this strings array? So, for example, for AB, we have 2 times AB in strings. So we are supposed to return 2 for AB. For ABC, it's just occurring once in strings array. So we are supposed to return 1 for ABC. For BC, since there is no BC in this array, we just return 0. So everyone got the question, right? The idea is basically, I just directly thought that map would be really, feasible for this question, since we need to know the occurrences of each string, which map already allows us to do that, and also the string itself as a key. Then I just thought that we can basically just insert them. I mean, find the frequencies of each string in strings, then just check. For example, once just loop through each queries in queries array, and then check if we have how many times we have AB so far, how many times we have seen ABC so far in the map. This is the idea. Let me just show the steps. Like for example, for string, you just loop through each string and set for this is keys and the values.
Just to be clear, can you put the example on the board that you are going to run?
Yeah, I'm gonna run here.
Yes, can you put the example on the board as well? Like the slide might not be
Okay.
visible to everybody. Let's put the example.
These are strings and queries. BC. So first, you just keep track of how many occurrences do we have in the strings. So for the AB, we just once loop through this, okay? For AB, we have 2 times AB, right? So we say 2. And for ABC, we have only once. Once we have this data structure, we have keep track of this value, then now we can loop through and check how many times we have this. For example, for AB, we just check if there is AB in our map or not. If there is no any AB, actually let me also result. For AB, we have 2 times, we have 2 counts of AB, so we just set 2. For ABC, we have only one ABC in our map. And for BC, since we don't have any BC, we just check if there is any BC or not, so we can say 0. That's it. And for time complexity analysis, I think since we just look through this array only once, and for checking once, it's gonna be OR. And for memory, since we use only result array, since we have only using result array as an extra memory, it's gonna be also OR. Where ends the number of strings, let's say. Or and one thing is we are also using map. Yeah, or extra memory map and the result.
So can you tell us more about the extra memory that the map is introducing?
Yeah.
Is it just the number of strings in the array or
No.
something more?
It's actually, guys, it's the number of unique strings. I mean, for each string, for example, we have 2 times AB here, but we just keep track of once. So I think it's gonna be like the number of unique strings that we have in strings.
And what's gonna be in the worst case?
If we have all the unique strings, let's say A, B, C, D, or something, it's gonna be of n. Where n is the number of the strings in strings array.
Are you sure, or is there one more variable that we should consider?
We have also values.
How about the length of the string keys? Isn't,
Yes.
isn't it the memory that is required for a string is,
Yes, yes.
right?
Yes, so we should also consider, like for each query, since the length at most 20, we also multiply by 20. Yeah, it's gonna be like n times 20.
Yes. So Tim, at the end of the day,
Forget.
like in an interview, the analysis you are making about time complexity is not just the asymptotic time complexity analysis. It's not like you are given a problem in the exam that you have to find the right answer and there is only one right answer. No, the explanation you are providing is very important. So let's say when you were covering such kind of problem and you were giving the time complexity analysis like this, I don't think this would be very satisfying for your interviewer. So what they really try to see is how you are approaching to the logic behind. So with the last additions, Suha come to the right point. But we would expect Suha to get that from the beginning. Because the code was there. I mean, it's obvious that there was map here and it has strings in it. And for each string, we know the length of the string definitely matters in the orders of how much of a space it's going to take from the memory. Right? So the earlier you start paying attention to these type of things in your time-space complexity analysis, the better you will get.
And one correction is, sorry guys, since those arrays are different, might be different than each other, they say it's not ON time complexity, it's ON plus M. Yeah, sorry. I mean, if those are same, you can say, but since it's different, yeah, sorry.
When we are creating the map, shouldn't we use the query list or the query to create the map, since if we are trying to access BC, it's going to be key error since it's not in the keys. When you are searching through the queue, the query,
Okay, let me check.
use the string list to create the map.
Okay, so it says for each string. Okay, we should just change the order. So we are checking each string, as you said, not each. I think.
So if you use that, there's going to be repetitions in queries, and if you store the queries in the dictionaries, you won't have the values of the repeated queries.
But we won't have BC as a key to begin with if we
You
don't
can
have it.
validate that and
Okay.
create.
Yeah.
Why the
value.
extra validation? We could start with BC is 0.
What if you had AB, ABC, and AB?
That works, but AB must be added to the key instead of BC.
I'm gonna ask something. How do you, let's say we are supposed to check for each query, right? Not each string. Okay. So what if we didn't add those? We are not aware of those strings. How do we check if we have this in strings or not? How can we answer this question without knowing if we have this or not? We have to know beforehand to check to answer this question. That's why we are keeping track of those strings, not queries. It doesn't ask how many queries do we have in strings. It asks how many strings do we have. You got it?
Yeah, but like when we return, we are going to say BC 0, right?
Yes, we have already done.
Yeah, but how do we know from the map? Like, how
Because
do we-
since there is no BC key here, we can just check if there is, like, you can just think as if this is a basket, okay? If there is this one or not, you can check it, right? Then you can say there is no BC, then say 0, that's it. If there is, you just need to supposed to return value if there is. That's it. You get it?
And Tim, how do we check whether a key exists in a map in your favorite programming language? Are we all clear with such utility functions? So we know how to do them, right? Okay. So yes. Okay.
And one more point is, guys, since we are also supposed to find the how many times question, that's why we are using map. If it was just asking if this is in this list or not, then we could have used set, for example, for this purpose. But right now since we also need the values, the occurrences, it's really better to use map for these situations. Yeah.
So, is everybody clear with the approach? I think so. Okay, any other approach? As a different solutions?
Okay, how about this? Let's say we are not allowed to use extra memory. Zero extra memory. Or constant, let's say, but you're not allowed to use something like a map. How can we do that?
Without extra memory, maybe using of n square.
Yeah.
It will be a very naive approach, but you can use an of n square approach of map. N times m. If the length of this array is m, and if the length of this array is n, so we can check each value of this list for all the values of this list. First we check AB, and we keep the count and values this array, and we continue for all the values of the second list. But it will be very useful compared to the hash map solution. So there is a trade-off between
Yes.
time complexity and space.
And is there a variable that we are forgetting here? Like again, I think you kind of assume that the string length is constant, but there is no guarantee, right? So it would be better to also add it as a parameter. Right now, n is the length of S, and m is the length of Q, right?
Yeah.
And we can say k is average length of each string, and say our time complexity is n times k. Or it doesn't have to be k, I mean, you can define a new variable, but we should keep in mind that the length of the string also matters. But overall, like the relationship you are talking about, it's a very good one. So team, as you see, by getting some extra memory, we can decrease the time complexity, and vice versa. And sometimes in the interviews, they can even ask you to find dumber solutions like this one. Like hash map solution is way better, right? But what if the conditions are different? What if you have too many elements that, or what if you have some memory requirements, you should allocate an extra memory. You should still be able to come up with solutions, right? That's what you have done. Thank you.
Is that not using extra space? Aren't we appending to a list or something when we find the count of that first string?
Well, let's say if this was passed to you as a parameter, like basically when we are calculating extra space, we kind of don't count input and output as extra space. Yes. Or like you can state it, you can say, hey, if we are going to count this, then it's going to be ON, like or M, because result has the length of the Q array, right? Like since it's explanation, you can make it clear, and it's better to do it in the interview.
One addition solution is very quickly, as Caleb mentioned, I think I now get it. We can also, guys, we can also start from the queries. For example, we will just say we have AB, ABC and BC. We just look through. Then we check, do we have AB? Yes. Then increase it. Do we have AB? Yes. Then increase. Do we have ABC? Yes. We can also do this, by the way. Just kind of reverse.
So reversing.
This is what you mentioned, right? Now I get it.
Okay. So
I'm not sure if I didn't also, I mean, the analysis extra space. Can we do this with quick sort in place, with random pivot, and then use two pointers in each of the query and string itself?
okay, first we sort the. Okay, can you show us the solution?
So we sort both of these with quicksort in place. I mean, I guess we could sort other analog and sorting algorithms with in place, but with quicksort it should be random pivot. And while these sorted, you go from the query array and then you proceed here and count how many elements correspond to this and then while you finish this, you go here and move again, and then count how many elements are there that correspond to this M log n. Sure. I mean, there's string comparison. But string comparison.
Yeah, within all of them, so.
Yeah.
Once you should have to maintain the place of the query.
Yeah, it should be in place.
Yeah, the algorithm is in place.
What's that? What do you say? What?
The query will be sorted.
The query will be.
Since you are going to.
Yeah, both lists are going to be sorted.
Yeah,
But the output depends on the.
Oh,
But also, do
the
you have to
output have to be based on this sequence. Like two, based on the query. The value here 2 is for A.
Yeah, we shouldn't
So
change
if
those.
Oh, I see, I see. So you need the original orders. Yeah.
Okay. So one thing I want to mention on this question is, like, after getting the n-square solution is I think easier. Then finding for the bottleneck is necessary after that. So what was the bottleneck for this problem? Checking if how many times this string is in the string array, right? So for each query we are looking the string array n times. So we are doing repetitive operations here. We already saw if ABC is in the string array when we check for AP, but we are repeating it because we are not keeping track of them. So what it does is just pre-process the string array, so we can we don't have to do repetitive tasks. So in interview environment, like doing such pre-processing on the inputs will help to improve our solutions. I think that's clear. Any question? For the third question, want to try?
Let's start with like who solved it? Can we see hands? Who solved it in the contest? The third problem. It's okay to solve. It's a good thing. Okay, so do we have only one person? Can we see hands again? One? Did you solve it or not? Why are you looking at other people? You should know it better. You solved it. Okay. Would you like to give it a try? Thank you.
What the question says first, JC loves cookies. He wants the sweetness of all his cookies to be greater than value k. To do this, JC repeatedly mixes two cookies with the least sweetness. He creates a combined cookie with sweetness of 1 times the least sweet cookie plus 2 times the second sweet cookie. He repeats this procedure until all cookies in his collection have a sweetness of greater than or equal to k. And we are given the cookies in a list, and we are supposed to return the number of operations that could take to make the sweetness of the cookies in the list greater than or equal to the value of k. My approach is using heaps, a min heap. Min heap gives me the minimum of all the items in the list, so I could pop twice to get the least to the cookies with least sweetness. So I could operate this and add back to the list so that I have a better cookie with better sweets, and I have to count every time I improve the sweetness of the cookie. So we are gonna have a min heap.
So can we start with an example just to understand the question better?
Okay.
Maybe not everybody had enough time on the problem.
let's say we have this, and we are given k of 7. What we are asked is to make all these cookies which have sweetness of less than 7 to be greater than or equal to 7. And what you're supposed to do is get the least sweet cookie and the second least cookie, the second least sweet cookie, and add back to the list using the operation of 1 times the first sweet cookie plus twice of the second least cookie. So the approach is we'll get 1, we pop that, and we will also pop the second least sweet cookie, which is 2, and this is 1 times 1, 1 times 1, and we have to multiply twice the second. This is going to be 1 cookie. This is a reaction, and this gives us 5. So still, we haven't maintained the condition, which is the sweetness of the cookie should be greater than or equal to 7, and we keep doing this until all of the cookies have a sweetness of at least 7. In this case, every time we operate on the cookies, we have to maintain the property of the heap, which is it should be a mean heap, which have the minimum element on the first index, like so. If ultimately we should have a number here which is the least from all of its children. So let's maintain a mean heap. When we start, we can just heapify the list, and that makes the list a mean heap with the minimum sweet cookie on the top. We can use, I solved this in Python, so we can use a package called heap_q. Let's see, the input is A. Which is a list of sweetness of the cookies. And we heapify A. And since we have to keep count of how many times we mix the least sweet cookies, we can have a count variable which starts from 0, because it could be already guaranteed to have that condition. So we have to count the number of operations, and what we have to do is until we have no cookie with sweetness less than k, we can keep doing that, and also at the end we could run out of cookies so that we don't have anything to mix with. So the case is find the mean heap as 0. This giving me the least element in the list. Actually, this should be this is our case. Until this is not maintained, we should keep mixing cookies. So let's say the first list from the list is heap to the heap hop. this hopping function guarantees that when we pop from the list, we always get a minimum, and also the property of the heap is also restored. Or it's simplified again. Now, what we have to do is we have to multiply the first by 1 and the second by 2, and we add back to the list again. And this gives us the count, and we might not have achieved our condition, so we have to check at the end. We have to check we haven't run out of cookies without satisfying the condition. So we can say return count if as we return, if we are not able to do that, we return -1 simply. So this is how I solve it. Any questions?
So are we all familiar with the heap methods right now? It's a relatively speaking new topic, right? It's been just a few days. So are we all clear with its methods, or do we need more practice time to understand it better? Probably the second, right? So in that case, like if you are not feeling very comfortable at the moment, if the solution didn't look very clear, this is very normal. And like at the end of the day, there is no rocket science. After having more practice on it, once you get a little more exposure, after solving a few more problems, you're gonna understand it better. So it really depends. Like if you have some experience, obviously, it's gonna be very easy to process it. But for some of you guys, this might be a new concept, and for such concepts, it's normal that it's gonna take a while. So don't feel bad about that. You can feel your teammates. You can ask your teammates. You can ask your mentors. You can ask us to get to know more about it. But at the beginning, it's very normal. Then it's gonna start feeling better.
So 10 minutes.
I don't think we are using any extra space here. This packet operates on this array to fit any heap, and we are not maintaining any external or additional space, and that gives us O of 1 or constant time. But the time is every time we did this operation, we are decreasing the number of elements by 1. So in the worst case, this could go for the length of the array, which is O of n. And in this, we are popping an element and also maintaining the invariant of the heap, which is we have to maintain, after we pop, the list element is always at the top. And we are doing it twice, which this takes logarithm of n. This also takes log n. So it's O of n into 3 log n, which is the O of n log n.
What's the heapify function's worst time complexity?
Worst? The worst
Time complexity.
The worst time complexity of heapify could be O of n. But it could not be O of n because heaps are full binary trees. You can't have degenerate trees. You have to fill the labels before you could go down the tree. You can't have this type of heaps. You can only have like this. And the worst case of heapifying is traveling all these labels, which is log of n.
The worst case of heapify should be log n, right? Not no log n, just n, as far as I know. It has not a simple proof for O(n) time complexity, but it's not n log n. So, like intuitively, you would expect it to be n log n, right? What's that? Just full heapify for the full array. It's just log n, you say. Are you sure? I don't think
No, this is just for
It's
one.
already
Just for one.
Yeah, just for one. Not fully.
Okay, then let's use the terminology correctly. So if you are adding an element, then the complexity is log n. Because if the previous version was heap and you are introducing one new element, then the complexity is going to be O(n). Sorry, O log n. But if you are heapifying, when we say heapify, you can run heapify on any kind of random array. And it's going to make it like heap. So it's going to do the operation so that if it's a min heap, the minimum element is going to go top, and every node is going to satisfy the heap property, which is you're either greater than both of your children, if it's a maxi, or smaller, if it's a min heap, right?
basically this gets added to n log n. We did this once on the first before doing any looping. We have to maintain the mini environment, so this takes also n log n. So that makes this 3n log n plus n log n, which is 4n log n.
Cool. Thank you. And the next question is also heap question, right?
The last one.
The last one. Oh, this is 3 and there is also 4. Okay.
So I think the question is easy and clear to understand, but understanding how heap works and using the built-in libraries in our favorite programming language is the struggle, I think, since we didn't practice. So please do that. Check your language's implementation of heaps and be familiar with the methods, how they work. So after that, it's easy to implement such functions.
Maybe one question she asked me if L2 might not be greater than K. I mean, it might be greater than K, so we need to check that function on that problem. Since we only are checking the first element in the array, in the heap, we need to check the next element.
For this one, right?
Yeah.
We are saying if it's greater than 1, which means 2 or more. So wait, do we need to
Just always have to combine the least two with the second least two. So it doesn't matter if it's the precondition is every cookie has to be greater than as k sweet. So if the second element we have is greater than k, doesn't matter. We still have to combine because we have another cookie whose one is less than.
The second key is not going to be less than
Is it good or shall I?
And Tim, like, do we want a quick recap on heaps, or are we able to understand what is going on? Who wants a recap on heaps? Okay, so looks like a short recap would be helpful. Heaps are super useful if we are looking to find smallest or largest in the group. And sometimes the questions can be in the form of second largest, second smallest, or as in the case of the last problem, median. It might be looking for somewhere like not at the beginning or at the end. And even for such problems, there can be some heap applications. But to get there, first we need to understand how this data structure is working, right? And heaps are full binary trees. Was that called full? I keep mixing them. Full or complete? Complete binary trees? Okay. So what does it mean? It means when we are adding a new node to the tree, we are adding the most intuitive one. So let's cover this with an example. Let's say this is our tree. Where would you add the next node? Like if we are going with order, you would probably add it here, right? And the next node, if I ask you to add it with the order, you would probably add this one. And if you want to keep going, it's going to keep growing like this, right? So this is called complete tree. And heaps are complete trees too. So there are things that are beautiful about complete trees. For example, we can indeed store them in an array. So now let's try to have some sort of numbering mechanism for these nodes. So let's say our root node's number is 0. And then let's say we are numbering them as we inserted them into our tree. So now let's add more to see if there is a pattern that we can notice. So given a node index, how can we calculate our children indices? So you're going to be given index of the node, and our objective is to find out what are the indices of our left and right children for the given node. Yes?
2 times n plus 1 and plus 2.
So if n is the node number, right? Then 2 times n
Plus 1.
mm-hmm.
And 2 times n plus 2.
n plus 2, right? So now let's take a look. Here, n is 0, and the formula says this is 1 and this is 2. And here, n is 1, and the formula says it is 3 and 4. Like as you see, your both children, the difference between their number is 1. Because that's how we number things, right? We started from 0 and we numbered them with their order into coming into the tree. So up to this point, are we clear with the numbering scheme and what kind of tree structure we have? So on top of this structure, the tree, the heap has conditions for the values of the nodes. So now let's imagine if we have the guarantee that every single node in this tree has a smaller or equal value than its children, then where would we have the smallest element? So now let's fill it up. What was the condition? First, every node has a smaller or equal value than their children. So now let's add some values. If this is 10 here, can I have 9 here? No. The reason is, it says, hey, every node has to have smaller or equal to value than their children. And 9 is smaller than 10, but 9 is child of 10. So that's why we are indeed breaking our rule here. So the numbers coming here, they should be larger than 10. Let's say this is 19, this is 11. Do we have any rules for nodes that are in the same level? Like here is the rule list. Do we have anything? No. It just says every node has to have a smaller or equal value than its children. So now let's see. This is 19. Can I have 35 here? Yes. Can I have 15 here? No, because it's going to be smaller than 19, right? So this cannot be 15. Let's say this is 35. And let's say we have 15 here, 19 here, 40, 41, 45, and 37, let's say. So, is this a heap? How do we check? Our first check, actually, it comes from the structure. So now let's add it here. So we said this is our second condition. Our first condition is, it has to be a complete binary tree. So is this a complete binary tree? Yes. What if I delete this node? That wouldn't be, right? I have to remove these guys as well. So now, we understand under what circumstances a given tree can be a heap or not, right? So with these two conditions, indeed, this becomes a min heap. What do we mean by min heap? By min heap, we mean that this heap has the smallest element in the given ones at its root, on the top. So that's why this is min heap. So how can we make this a max heap? Any ideas? Any suggestions? It's not like we are just going to change the set of rules. It's not like we are going to try to convert this into a max heap. We are going to change the set of rules. How can we set new rules that it's going to make sure we are going to be constructing a max heap? Any suggestions? Suggestion? Every child should be less than its parent, right? So from the root's perspective, or from the parent's perspective, the parent has to be greater or equal to, or we can just say greater, right? Since we put equality on the other side. So if we had said, instead of smaller, if we said greater, then this is going to be a max heap, right? So now let's try to make a small example of it here. So let's say we have 5 elements in our tree, and this time we say every node has to have a greater value than their children. So if this is going to be 50, can this be 60? No. Let's see, this is 40, this is 15, this is 25, and 5. This would be a max heap, and this would be a min heap. So now, are we clear with what are these? Like when, let's say, you are given a tree, can you check that whether it is a heap or not? Now we are clear with that part, right? Okay. So now let's try to add on this. Okay. So now that we know these definitions, the first operation that we can consider is how to add a new element. So let's say there is a new element that is coming, and we want to satisfy our heap property. So first off, where would you add this new element? Let's say we are going to introduce a new element to here, to let's say this heap. Like this one right now, representation is not very nice. It's going to be added here. I don't want to remove it, so let's add here. Where is it going to come if I'm introducing a new element? Below 15, right? Because this is going to be a complete binary tree, right? So it has to follow the order. That's why this node is going to be filled up. Let's say the new coming element's value is 60. Are we heap anymore? No, because this node does not satisfy our first condition. This node does not have a greater value than its children. So then what can we do? Is there anything else that is causing trouble with our heap properties? Like if, assuming before we were heap, only the new node can introduce a problem, right? And that's exactly what's happening here. So how does it introduce a problem? We added an element in the max heap that is greater than its parent. So how can we fix it? We move it up, right? Because if this guy is greater than this one, this deserves to be in here. That's why we swap them. So this guy becomes 15 and this guy becomes 60. So now, is this a heap? Is this a max heap? Not yet. We still have a guy that is causing trouble. So it was this guy before, now this guy is causing trouble. Now this guy is not greater than its children. And again, we have the same cure, right? We can just do a swap operation between them. And then this one is going to become 50 and this one is going to become 60. So now, can we generalize on this logic? What did we do here? When we add a new node, we just checked whether this new node is breaking the heap property by comparing its value with its parent value. So now we had the formula here. to go from parent to the children, right? So now let's also study the other way. So how do we go from n to its parent? Given n as our node, no. What is our parent's node?
Over 2.
Over 2.
Yeah, for example, for the left child,
How about for the right child?
2 times n plus 2 over 2.
Suha, you said this is going to be over 2, right? So this is your suggestion.
I mean, we just add over 2 for the below formulas.
So Suha, what needs to come here? That is the question.
Okay.
You are given your node number, and then our task is to find out what is going to be our parent's number. We want to reach to our parent's number. Any suggestions? Yes.
n minus 1.
N minus 1 over 2, right? So now let's give it a try. Here, 1 minus 1, it is 0. Over 2, 0. 2 minus 1, it is 1. 1 over 2. We do computer division. So it is 0. And let's take a look at here. So 9. N minus 1 over 2. 9 minus 1 is 8. 8 over 2 gives us 4. And 10 minus 1 is 9. 9 over 4. 9 over 2 also gives us 4 in computer. So are we clear with this? How can we go to our parent's number? Cool. So now back to here. So if we know our node number, we know our parent's node number too, right? With the help of this formula. So now can you compare your value with your parent's value? Right? You can have helper functions, which is going to give you your parent's node value. Your parent's node number. And with the help of that, you can compare the values. And if your value is greater than your parent's value, then you do this value. That's what we have done with this 60 at the beginning, first here, and then up here. And you can go till root in the worst case, if you have the largest element that is just introduced to the heap. So are we clear with this part? Any questions? Okay. And I guess adding an element to the min heap is going to be very similar. Do we have to go over that? Or is this clear to you as well? We are clear? Okay, cool. And now let's take a look at the removal operation. So where can we remove an element easily from a heap? From the bottom it's going to be very easy, right? But usually in context we are supposed to remove elements from the top, from the root. Because if you are keeping track of heap, and if there are some update operations, usually you are losing the element that you are looking for. It's either the minimum or the maximum. But you made a very good observation. It would be very easy to delete from the end, right? So when we are deleting from the top, what we can do is, in order to keep the structure as it is, we can get the latest element and put it over here. Let's say we have to report 10 for some reason, and it's going to be removed from our heap. So 10 is gone. And in this case, in order to keep our complete binary tree structure, we can only delete this last node, right? And when we do that, obviously we are not going to get this 37 disappear. It has to stay. And at the beginning, where can it go? This is the only place that's available, right? So it can come up here. So when it comes up here, this time we are in the min here, by the way. This is our maximum. And this is our min heap. And now we are at the top. So is this a min heap anymore? No. Then this time what we have to do is kind of the opposite of what we have done over there. Somebody has to go down. But there is one difference. Because when we are going up, there is only one parent. You only look up your parent, right? There is only one. But when we are going down, things are a little bit more tricky. Because we have two ways to go. We may have two children, right? There is no guarantee you can have 0 children, as in this case, or 1 children, or 2 children. They are all possible. And if we have 2 children, we have to choose which direction we are going to go. And if we are min heap, which direction does your intuition tell to go? Is it going to be always left? Is it going to be always right? Is it going to be small one? Is it going to be big one? What does your intuition tell? So anybody's intuition is speaking at the moment?
Small one.
Small one. So you want to replace yourself, you want to swap yourself with the smaller one, right? Among our children, if we are min heap, which children should come to the top? Like in a min heap, smaller one deserves to be on top, right? So that's why we are going to swap ourselves with the smaller value. So now, when we look at 37, with the help of this formula, we get access to our children. And among our children, we choose the smaller one. And we swap ourselves with the smaller value. And what happens is, 37 comes down to here, and 11 goes up here. And right now, for whom do we do the same check? This guy, right? Because it may still have to go down a little more. We don't know, there is no guarantee. Okay, so we save the root. Now this part looks good, so this is smaller than this and this. But what if this is still causing trouble with its sub-tree? There is no guarantee, right? So that's why we have to check. And until when we are going to keep going and swapping? What's going to be our end condition?
Leaf node.
Either hitting to leaf nodes, or can there be another condition where we should stop?
If you cannot find any smaller than us, maybe.
Yes, like when it reaches to its natural point, which is it's going to be smaller than both of its children, then you can stop. You don't have to reach to the leaf level, right? It really depends on the input and where we are. So are we clear with this logic? Okay, so now how do you guys feel about heap? About the inner working mechanism? So when it comes to data structures, guys, I completely suggest at the beginning making your hands dirty and go ahead and just try to implement the data structure itself. So it's not like their complexity is going to get quadratically more complicated. No, we don't have super complicated data structures that are coming on your way. No, heap is one of the most complicated ones that are handy for interviews, right? We can ask our group 1 members. So what other data structures would you say they are complicated like heaps? Tries, right? Maybe. And it's also, I would say, I would put it in the same level with heap. It's like trees, and it takes a while to maybe internalize the working logic of it, but then they are very handy. You feel very comfortable playing with them, and they are useful. So same with heap. So it's not like it's gonna get worse and worse and worse. No, guys. So this is harder than stack and queue, right? Like once you think about it, the harder logic. So yes, it will take a little more time, but this is kind of the level in terms of data structures that we are going to reach to depth. Like of course, there are more complicated data structures that are like AVL trees. Maybe you guys heard like red-black trees. There are some complicated operations or like B+ trees which are very popular in database systems and stuff. But they are not in our scope. They are not super useful for the interview context. That's why we are not going to go to those waters. For us, this level of detail is usually enough. Cool. So now, finally, let's think of the cost of these operations. So first off, right now we didn't see how to build a heap from normal array. Did you guys cover it in the class? Heapify operation, like given an array, how you can make it a heap. Maybe for now we can skip this. I'm not sure if we will ever need that, but for now we can skip this. But we have covered 2 operations here, right? Inserting a new element to the heap and removing an element from the heap. And once you think about it, if you can implement these 2 operations correctly, you can start with an empty heap, and it is guaranteed that you will have an heap at any given time, right? Because it's not like you will start with an array and convert it to heap. Even if, let's say, that is the case, you can create a free new heap and then start inserting elements from the array one by one to this heap. But this time your construction complexity is going to be n log n. Because every time you are adding a new element to the heap, which we are going to cover its cost right now. Okay, so now let's take a look at time and space complexity of these operations. Let's start with insertion. Any guesses? How long does it take to insert a new element to a heap?
Okay.
Log n. And the reason is, we insert it to the bottom, right? And we know that the depth of the tree is log n. And then in the worst case, it can go up to the root. Maybe the new element we inserted is the smallest, so it may traverse up to the root, right? So this is going to give us log n time complexity. How about removal operation? Same, log n, right? So likewise, when we remove an element, let's say this 45 went up to here, it might have to go down again here. Maybe it's the largest element, so it's going to go all the way down to the leaf nodes. Okay, so I guess now we feel more comfortable with this. And finally, let's say you are given a heap, and your task is to sort the elements. Like you are given an array with elements, and you are given a heap, working heap. How would you sort them?
I would maintain a heap, and I would pop the minimum element till the heap is empty, so that I end up having a sorted.
So at the beginning we had array, and then what did you do? So our heap is empty at the beginning.
Yeah, I heapify that first.
Okay, so let's say there is no heapify function you can call. You have the heap that is given to you and the array, but there is no heapify function.
I add every element in the input list to the heap, and after adding the elements, I pop the minimum element every time.
Yep, that's a very elegant solution. So basically we can insert all the elements we have in our array into the heap, right? And as a result, what we know about heap, is it going to keep them in a sorted order? No. If we traverse heap, can we generate sorted order? There is no guarantee, right? But what we know is, hey, the top element is always going to be the minimum or maximum, depending on whether we use min heap or max heap. Let's say we are using min heap, then we know that the top element is going to be always minimum. And if you are sorting elements, if all the elements are in your array, and if the top one is the minimum, what can you do? You can just get it and put to the beginning of your output. And then do the same operation again until you run out of elements in the heap, right? Because it always gives you the smallest element among the ones that you currently have in hand. So that way you can indeed do heap sort. And what will be our time complexity with this approach? N log n, right? Now let's think about it. First we are inserting all the elements into the heap, right? How much time it's going to take? How many add operations do we do here? How many insert operations do we do here? N, right? And each of these operations are taking log n time. So as a result, the total time complexity will be n log n when we insert everything into the heap. How about when we remove them one by one and construct our output array? It's the same thing, right? We are going to do n removals. Each of them are costing log n or O log n. Let's say some of them are going to be cheaper, obviously, as the heap gets smaller. And as a result, our total time complexity is going to be n log n. Cool. So team, heaps are very elegant data structures, and they are going to keep coming on our way. Sometimes some problems, they are eased a lot by using a heap. Maybe sometimes the solution is not going to be just using a heap, put everything to heap and then get. But using a heap might make your life a lot easier. So I highly recommend playing with them, like try to implement. If you get the logic right now, you should be able to give it a try to implementation by yourself. And with this logic, since we have this ease in numbers, you can indeed keep heap in an array. Like look at that, the numbers are like, it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we keep building new elements, 10, 11, 12, 13, we never skip an element. So you can keep them consecutive. And just one array can be enough to keep the whole heap structure. So is this last part clear? Are we able to follow? So this one in memory will be represented like this. So we are going to have one array for the heap. 0, 1, 2, 3, 4, 5, 6. Let's say we are going to fill it up to 7. Maybe this is 27. Should be fine. And 15, 19, and 10. And with the help of these formulas, right, you can easily have some helper functions. Or you can hard code them, like it really depends how many times you are going to refer to. And with an array, you will be representing a heap. So that's why they are also very elegant. Like even if it's a binary tree, you don't have to do tree implementation to maintain a heap. And again, team, I don't expect you to implement heap in your life many, many times. Obviously, your favorite programming language should have something similar, either a priority queue or heap. So you're going to be using that. But if you really want to internalize the logic, if you want to apply it effectively on the problems you are going to be facing in the future, it's better to go inside and see how this data structure works under the hood. So that's why I highly recommend everybody to try to implement heap by themselves. On an array with the helper function, let's see how the data structure works. Let's do heap sort with that. I think it's going to be easy that way. Do we have heap sort in the sheet? Okay. Maybe we can add heap sort, but for the heap sort question, let's say we are not allowed to use a built-in heap. Okay? So we are going to build our own heap. And let's get our hands a bit dirty. Cool. Thank you very much.